All right, acids and bases. We're going to talk about self-ionization of water and what is really meant by pH. Things to keep in mind as we go through this screencast. How do scientists measure the concentration of hydrogen ions in solution? And how do we solve pH problems? Okay. So, self-ionization of water. Water, pure water, is going to self-ionize, meaning it's going to go into ions. It's a very small amount, but it does happen. When it does this, it forms hydronium ions and hydroxide ions. So in solution, two water molecules, one is going to act as an acid to give up its proton and form the hydroxide ion. The other water molecule is going to accept that hydrogen ion and form the hydronium ion. Okay. Shortcut is just to write it water in equilibrium with an H plus and a hydroxide. This symbol here means that this reaction does not go to completion, meaning there are some water molecules left and there are some of the products, the hydronium ion and the hydroxide ion, that also exist in solution. Okay. The product of the hydronium ion concentration and the hydroxide concentration is constant for all aqueous solutions. Throwing a new symbol in at you, this symbol stands for molarity. Okay. So the concentration of the hydronium ion in moles per liter times the concentration of the hydroxide ion in moles per liter is constant for aqueous solutions. Okay. It is called a Kw, and it is equal to that concentration and molarity of the hydronium times the concentration of the hydroxide molarity. That constant is 1 times 10 to the negative 14th molarity squared. Right, so I just explained the brackets, and again, this hydronium ion and the H plus is used interchangeably. This is really a shortcut. In solution, that H plus really exists as this hydronium. So the hydronium ion is truer to what really exists in solution. All right, so neutral, acidic, and basic solutions. Remember that Kw, that 1 times 10 to the negative 14th molarity squared, is always true for water and for water solutions, always. So for pure water, hydronium concentration equals the hydroxide concentration. Because remember, if water is self-ionizing, for every 2 molecules of water, I get 1 hydronium and 1 hydroxide. So because water is splitting, those concentrations have to be the same. For acidic solutions, my concentration of the hydronium ion is going to be greater than that of the hydroxide. For basic solutions, the hydroxide concentration is going to be greater than the hydronium solution. However, for all 3 aqueous systems, pure water, acidic solutions, basic solutions, this relationship is always true. Hydronium concentration times the hydroxide concentration is going to be equal to 1 times 10 to the negative 14th molarity squared. All right, so what is this pH? Well, pH is a way to represent hydrogen ion concentration in solutions. And you should, I think, already be somewhat familiar with pH. You probably know it as a scale of from 1 to 14, and 7 being a neutral solution. But what does that really represent? Well, it's a negative logarithmic scale. So pH is equal to the negative log of the hydronium concentration for a solution. That's an important piece of information right there. So for each increase in 1 pH unit, it represents a decrease in the concentration of the hydronium ion by a factor of 10. Okay? because that negative is there. An increase in a pH unit represents a decrease in the concentration. Okay, so the greater the pH gets, the more basic it gets, the solution gets. Why are we using pH? Because when you talk about the hydronium concentration, the concentrations are very small, 1 times 10 to the negative 14. You don't really want to say 1 times 10 to the negative 14 all the time. So pH lets us work with these small values, and we call it like, 6.2, 3, 8.14. They're easier to work with than the exponents. Neutral solutions, pH is 7. Acidic has a pH less than 7. And basic solutions have a pH greater than 7. And this table just gives you an idea of what some solutions are. Lemon juice is acidic, black coffee is acidic, sodium bicarbonate seawater is basic, milk of magnesia is basic, washing soda or soap is basic. All right, so what is the pH of a solution where the concentration of the hydronium is equal to 0.000059? Well, here are several equations that we are going to use. You should write these down. So pause me so you could write these down in your notes, because these would be important to have in your notes. Did you write them all? Good. The one we're going to use for this problem, pH, where I'm given a concentration of hydronium, is going to be this first equation. pH, this is my given, so I can find pH if I just take the negative log of that concentration that's given in the problem. If you do that, it's 4.23. In your calculator, if you have the style calculator, if you don't have the style calculator, see if you can find it. If you can't, come in and talk to me. We'll find it together. All right, so on your calculator, you're going to put in the negative, then you're going to do log function, and then type in the concentration of that hydronium. Significant figures, because I can't leave this alone. Number of significant figures in the concentration is going to be the number of places past the decimal point in the pH. This has 2 significant figures. That means I go to 2 decimal places past the decimal point. Okay? One more problem. What's the pOH of a solution that has a hydroxide concentration of 0.0039 molarity? Excuse me. We're going to use this equation. pOH is equal to the negative log of the hydroxide concentration. Very similar in the calculator. Negative log button, 0.00039. You should get the number 3.41. Make sure that when you put that in your calculator, you get 3.41. Okay. So working backwards, what is the hydroxide concentration of a solution that has a pOH of 11.3? Well, what equation from that list? Oh, that equation from the list. Okay. Here I'm given a pOH and I'm asked for a hydroxide concentration. So I'm going to use this equation. How do I do that on my calculator, you may ask? Well, I use the shift button and then find the 10 to the x, okay, which is shift and then log, and then I'm going to punch in the pOH. So shift log, which give me 10, and then punch in negative 11.3, and you should get 5 times 10 to the negative 12th molarity. We'll be doing a table in class. That gives you a little idea of some of the math. Hopefully we can get the rest of it done in class.